Testing. 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 Me. Is it working? It is. Okay, it's a little bit soft, but it's working. Alrighty, welcome to another Hoopo stream. I'm still sleep deprived, but we're gonna do this. This paper is pretty important, so we're gonna have to get through this. So this is coming out on the 4th of July. I think this is actually a preprint. I'm not exactly sure, but I don't think this is the final version of this paper. I'm sure there'll be some updates potentially. But this is the paper that introduces SDXL. So what that means is the Stable Diffusion XL, XL like X large. So the big Stable Diffusion. But really it's kind of just the next version of Stable Diffusion. Stable Diffusion is a open source, in quotation marks, diffusion model that's very popular in the generative AI community. So the subtitle here, Improving Latent Diffusion Models for High-Resolution Image Synthesis. High resolution just basically means big width, big height. Image synthesis, right, creating images from the way most of these are conditioned is using text. And latent diffusion model, because it is a diffusion model which operates in a latent space. So it's not operating in the pixel space, it's operating in the latent space. So you got a couple different people here. I guess these are all people of Stability AI. And you got the code link and the model weights. So first thing to note here is that I went on Stability AI and I asked for permission for these weights. So I think it's, for example, right here. There's a bunch of different models, but you could say, for example, here XL base 0.9. And you have to sign this very long agreement here where I went ahead and signed it, but it's not really open source. You know, it's starting to get a little weird in the AI world where people advertise themselves as OpenAI or open source or, hey, we just released the model weights, but they are increasingly not doing that. You know, you have to sign this weird license where they can basically force you to do things. Like you can't use this in a commercial application. There's like weird rules, and you can't even use it. You have to like get access to use it. So I don't know. It's getting a little weird for sure. And nobody is really open source in the way that Linux is open source, or any other like Python package is open source, right? I feel like the definition of open source is being changed in front of our very eyes. Okay, so here obviously we have a bunch of pictures that are cherry picked, but even so, they're pretty impressive. So one thing to note here is in this cup here, weights got leaked though. Yeah, they got leaked, but if you were to do a startup and use those, they could still come after and sue you, so it's that kind of gray area where it's like things are technically illegal, but because nobody's enforcing them, they're not illegal. But if they ever wanted to screw you, they could screw you. So it's just not a good place to be. I'd much rather be in a situation where they just post them and you can go and download them easily. There's no strings attached and you can use them as you will, but even the Stability AI, which is supposed to be the kind of pinnacle of open source AI, and then OpenAI, which is now just kind of a joke that they call themselves OpenAI. Like all of these companies are now making it more and more and more sketchy, more strings attached, more licenses that you have to agree before you click on anything, and so on. Yeah, I'm definitely. So I mean, I say that, but I still signed the user license agreement that they put there because I'd rather have these weights and play with them than not have these weights. But okay, back to these cherry picked examples. Kind of what I'm looking here is in this cup, and then here on this guy holding this sign. this is perfectly spelled English. That's impressive. You know, a lot of these generative image models, they have trouble spelling signs and things like that. So a lot of times the text is a little bit nonsense, but here this text is perfect. So that's definitely a big improvement there. Then looking at these two people here, we see the realism, right? So very realistic looking pictures. It's not caricatures or drawings, right? That's relatively easy to do, but these kind of like super realistic pictures usually used to be only Midjourney, but now it seems like Stable Diffusion is also capable of generating that. And then this one's kind of interesting. This kind of shot from the back of a person and you can see the skeleton. And I think the reason it's interesting is because the anatomy is almost there, so you can see how it's almost like the text, right? How like where there's a threshold where at some point the generative models will be able to generate the skeleton, and the number of vertebrae will be perfect. The actual pelvic bone will be perfect. The number of ribs will be perfect. Right now it doesn't look like that, but it looks close, right? So it's kind of showing you the frontier of that as well, where at some point the anatomy is not just going to look correct, it's actually going to be correct, right? So even, for example, here, this grasshopper with these pincers, I'm sure if an etymologist or whatever the bug scientists are called, I'm sure if we had a bug scientist and he looked at this, or they looked at this, there would be something wrong, right? Like the exact configuration of these mandibles is incorrect, but, you know, we're getting there. All right, so let's get into it. Every dream. In the least surprising event ever, the weights are leaked. Yeah, but those leaks are always sketchy because it's like I just don't trust that people leak the weights without some kind of weird payload attached. You know, there's so much sketchy stuff that people can put in model weights. We present SDXL, a latent diffusion model for text-to-image synthesis. Compared to the previous versions of Stable Diffusion, SDXL leverages 3 times larger UNet. So that's probably where the whole XL comes from, right? It's just kind of bigger image resolution. The UNet is what actually takes the raw image and then makes it into that latent. So the bigger the two sides of the UNet, the bigger the input image size and the output image size. The increase of the model parameters is mainly due to more attention blocks and a larger cross-attention content. Okay, so more model parameters, more attention blocks, right? You can kind of just keep stacking attention blocks, right? That's the whole deep learning paradigm, is that you can add more layers and make it a deeper learning system. So, larger cross-attention content. You guys hear that baby? It's going crazy. Uses a second text encoder. So 2 different text encoders. Sounds kind of cool. Maybe they like average them or something, or like concatenate the encoded text using 2 different text encoders. That could be kind of cool. We design multiple novel conditioning schemes. So conditioning schemes are how you condition the removal of the noise. So you can condition it on basically text. That's the kind of go-to example where you condition such that it removes noise with respect to some prompt. But you can also condition it on a variety of things. So we'll see what they do with that. On multiple aspect ratios, we also... so they're training multiple versions with different aspect ratios. That's a little... seems like a lot of money for nothing. They concatenate them. Okay, so they're concatenating the texts from the text encoder. We introduce a refinement model, which is used to improve the visual fidelity of samples generated by SDXL using a post-hoc image-to-image technique. So this to me seems kind of like a... people will use super resolution models, right? They'll generate an image and it'll be kind of like small and grainy, and then they'll use a super resolution image to upscale it. This is the pattern that you see in Midjourney. So in Midjourney, you generate the images, but then you have the option of also upscaling, which is basically just increasing the resolution of the image, and that's done with a separate model. So it seems like this idea of a refinement model is now also part of the Stable Diffusion workflow, where you're going to have a separate model that basically just makes it bigger and probably more crispy. Maybe cleans up some of the weird lighting and artifacts or something. We demonstrate that SDXL shows drastically improved performance compared to previous versions and achieves results competitive with those of black box state-of-the-art image generator. Okay, so here's a little diss on Midjourney. They didn't actually want to put the word Midjourney in the abstract, so they called it black box state-of-the-art image generator, where black box refers to the fact that we don't really know what Midjourney's doing. In the spirit of promoting open research and fostering transparencies in large model training and evaluation, we provide access to code and model weights. Yeah. Is it though? Is it? They do have the code here, but I haven't looked deeply into it. Requirements PT2. I think this is PyTorch 2, and then this is PT13. So PyTorch 1.3. Deja Vu Sans TTF. Shots fired. Yeah. SGM. This new GitHub UI is a little weird. You can kind of go through the repo like this. They're using PyTorch Lightning here. You see that? PL Lightning. It's a very popular framework. Also OmegaConf, dude. Fuck OmegaConf. It's gross. It's the actual diffusion engine here. Initialize from checkpoint. Here's your actual training step. Shared step. Where's this defined over here? Get the batch, encode the images, and then get the loss. Self.log, they have their own custom logging pipeline here. Okay, I'm getting distracted. Robin always uses PyTorch Lightning. This codebase is a lot cleaner than the old official CompViz SAI repos, though, for SD 1.x and SD 2.x. Interesting. So you're saying that this is actually kind of a refactor, so it's built from scratch. I could see that because it's also right. They call this SDXL instead of SD 3.0, right? They could have called it SD 3.0, but they called it SDXL, which to me means it's separate from that. So I could believe that it's basically they hired some new person, maybe this guy Robin. They hired this person, and then that person implemented it, or a slightly different kind of stack from scratch that uses different dependencies. You're saying the YAMLs are configs, inference. So YAML is basically like JSON. It actually means yet another markup language, I think is what the 4 letters stand for, but basically it's a config language. Scale factor. This is the denoiser. Floating point 16. That's good. Why not uint? That means that you can actually probably quantize this if they're just by default using FP16. Autoencoder KL inference. Is that KL divergence? Here's your actual text encoder, frozen OpenClip. OpenClip is the text encoder that came out of the clip paper. They say they use 2 text encoders, right? So what's the other text encoder? Okay, let's actually look at this paper. Oh yeah, you're right. I'm sorry. I'm looking at the old ones. Here you go. Conditioner config, frozen OpenClip 2, and frozen clip. And then here you can condition with some kind of time step embedding. So both of the text encoders are a variant of the frozen clip. It's not like they're using a completely different text encoder. It's some kind of open clip, but 2. See, this is a data set here, so this is the actual architecture and then the data set. The original sizes, tuple, and crop chords left are new, the paper discusses. Size as tuple. Okay, I mean, let's go back to this, though, because I still don't even know what half the stuff they mentioned here refers to. Last year has brought enormous leaps in deep generative modeling across various data domains. We focus on the latter and unveil SDXL, a drastically improved version of Stable Diffusion. Stable Diffusion is a latent text-to-image diffusion model, right? So condition the diffusion model with text to generate images, and it does so in the latent space. 3D classification, controllable image editing, image personalization, synthetic data augmentation. Okay, so a bunch of people have been using diffusion models for a ton of different use cases, is what they're kind of telling you here. Consistently surpasses all previous versions by a significant margin. I like this user study, so they're going to be showing pictures to people and then have people pick which one they want. This is kind of the machine learning equivalent of a double-blind placebo kind of study, so I think that's the way you have to determine quality for these generative image models. They have a bigger UNet backbone, which makes sense. You know, when you don't know how to make something bigger or better, you can always just try making it bigger, and then generally it becomes better. 2 simple yet effective additional conditioning techniques, which do not require any form of additional supervision. So, additional conditioning techniques, that's probably going to be this stuff here. This concat time step vector conditioning, they're calling it here. So crop coordinates, original size. So this is like extra special sauce conditioning that they're talking about here, which do not require any form of additional supervision. And 3, a separate diffusion-based refinement model, which applies a noising denoising process to the latents to improve the visual quality of its sample. Okay, so then you have the original pipeline, which will produce an image, but then you have this additional, what they're calling a refinement model. But interestingly, the refinement model is also a diffusion type model. And the way that they say a noising denoising process, it seems like it's basically going to add noise and then remove the noise. And then when it removes the noise, it'll result in a better image. Major concern in the field of visual media creation is that while black box models are often recognized, the opacity of their architecture prevents faithfully assessing and validating their performance. Yeah, so here they're kind of dissing on Midjourney again, right? The opacity of the architecture, the black box nature of the model. So they're really kind of harping on the fact that they open source their code base. Lack of transparency hampers reproducibility, stifles innovation, and prevents the community from building upon these models to further the progress of science and art. I wonder if this also applies to having unnecessary legal requirements and user agreements for getting the models, right? I don't know. Maybe you should think about that, Stability AI. Take that attitude and look at what you're doing. You know. I feel like this should just be a download button. It shouldn't be like a weird thing that I have to sign. These closed source strategies make it challenging to assess the biases and limitations of the models. I agree with that. And in an impartial and objective way, which is crucial for the responsible and ethical deployment. I don't think you can have both. I think either you subscribe to the idea that you have to limit the access to AI for responsible and ethical reasons, or you subscribe to the idea that lack of transparency and additional hurdles stifle and prevent progress in science. I think you can't have it both ways. That's the multi-aspect. They said OS on OpenRailM on July. EMAT tweet. with SDXL, we are releasing an open model. Open model, as long as you agree with our license, that achieves competitive performance with black box image generation models. Okay. All right, finally we have our first little model architecture diagram here. 2, improving stable diffusion. This is kind of a weird, this is not normal sections here, right? Normally you have kind of more of a background section. I was expecting a section where they actually just describe diffusion models, but they just go straight into the actual stable diffusion model here. So interesting, slightly different way of organizing a paper. Presenter improvements, there's modular. It can be used individually or together to extend any model. Okay, so you can use each of these separate parts. Well, the following strategies are implemented as extensions to latent diffusion models. Most of them are also applicable to their pixel space counterparts. So pixel space models different from latent models, right? Pixel space means that you're removing and adding the noise in the actual image itself. Okay, so what is this? Wins percent? Okay, so this is probably the way that they did the user studies. Yeah, so the users basically have to pick between probably 2 images. So 50% win rate means that they're picking it roughly 50% of the time. And here they're comparing it to previous models. So SD 1.5, SD 2.1. They're quite poor, to be honest. Look at that. They almost never get picked. And then here, this is the basically almost like an ablation here. You have the base model, which I think is just this part here, and then whether or not you're adding the refining step here, which is a separate model. The additional refinement stage. We generate initial latents of size 128 by 128 using SDXL. Afterwards, we utilize a specialized high-resolution refinement model and apply SDEdit on the latents generated in the first step using the same prompt. SDXL and the refinement model use the same autoencoder. Yeah, so here, this little purple square is the actual latent, right? So you see how this says latent here. If this was pixel space, this little purple square would be an actual image, right? It would be this more like this yellow square here that's 1024 by 1024. But the image is converted into a latent with this variational autoencoder that can take an image and turn it into a latent, or the way that they're using it, it takes a latent and turns it back into an image, right? That's what the decoder does, right? So in reality, this latent space is really just a language that a encoder and a decoder have learned to communicate to each other in. But in this case, they're not actually using the encoder for anything, right? Because they're starting from a noise. They're starting from a noise that is the same size as the latent, and then they use this unit here to basically iteratively remove the noise over a series of steps conditioned on this prompt here. So this yellow box here that says prompt, this is actually the text, and this is not just the text, it's the text, but also encoded with clip. So it's basically a vector that represents the meaning in that text. And here you just have base refiner, so both of those are diffusion models. So kind of the way that this looks, right, and then looking at the fact that this is a paper with a bunch of different people, it makes me think that what probably happened is they had multiple people working on different things, right? So there was probably one group of researchers that was kind of working on this, or potentially just one researcher, and then a different researcher that was working on this refiner model, right? I think when you see these pipelines that have multiple pieces like this coming out of a team that has like 10 people, generally what that tells me is that there's different people worked on these different pieces. So the fact that they're modular and can be used individually or together is also suggestive of that. They said open source as OpenRailM on July 28th, July 18th. Yeah, I'm looking forward to this model. I think it's going to be a good one. Starting with the seminal works of Ho and Song, which demonstrated that diffusion models are powerful generative models, the convolutional UNet architecture has been the dominant architecture for diffusion-based image synthesis. So again, the UNet is basically The reason it's called a U-net is because the letter U is very tall and then very thin and then very tall, and the U-net has that same kind of look to it. This is not necessarily the U-net that they're using, but you can see how it starts at a higher resolution here, and here this will be 128 by 128, right? Because they're doing it here in the latent space. And then it goes down, and here you have the compressed, also called a latent space, and then it goes back up. So these are kind of popular for other things too, like I've seen these for medical image segmentation is another technique that, or another application that people use. So this is a medical image segmentation here. You see some kind of slide with cells, and then here you have the final map, segmentation map. However, with the development of foundational DMs, the underlying architecture has constantly evolved by adding self-attention and improved upscaling layers over cross-attention for text-image synthesis to pure transformer-based architectures. Yeah, I wonder if they tried a transformer instead of this U-net and then it didn't work. Or is the U-net transformer-based? Shift the bulk of the transformer computation to lower-level features in the U-net. Oh, so they are doing that. Okay. So this is not, they're not going to be using a convolutional U-net. They're going to try to make it as much of a vision transformer as possible. We use a heterodistribution of transformer blocks within the U-net. So heterogeneous means mixed, right? Homogeneous means the same thing, and then heterogeneous means different things. So heterogeneous distribution means that these transformer blocks are going to be mixed in with some of the U-net that's more kind of convolutional in nature. Highest feature level, use 2 and 10 blocks at the lower level. Remove the lowest level in the U-net altogether. See Table 1 for a comparison between the architectures. We opt for a more powerful pre-trained text encoder that we use for text conditioning. Yeah, and I think there was other papers that we saw where basically in any kind of text conditioned image generative model, people have found that improving the quality of the text encoder is actually very important for the final quality of the image. So it makes sense that as part of this research, they would try to use the best possible text encoder. Specifically, in this case, they use 2, right? So they're going to use this one here, OpenClip VIT Big G. Okay. And then clip VITL. So 2 kind of clip variants. I feel like it would have been cooler if they used a text encoder that was different. I feel like that would have been cool if they used one clip one and then a different one that was completely separate from clip. Because at the end of the day, both of these text encoders, because they're both clip, right, they're both representing the same kind of data set that they're trained on. I don't exactly know if OpenClip and clip were trained on the same exact data set, but I suspect they were. So that would have been kind of cool if they used 2 very different text encoders. Okay, but they're going to use both of these text encoders, and then they're going to just concatenate the outputs and then pass that in to condition the diffusion model. Besides using cross-attention layers to condition the model on the text input, we follow 30 and additionally condition the model on the pooled text embedding from the OpenClip model. So cross-attention versus attention. I've described this before, but cross-attention. Yeah. Wow, this is actually the better picture. I used to show this manually, but cross-attention is whenever you're performing the attention calculation, right, which has queries, keys, and values. There's 3 different matrices there. And cross-attention means that you're using different sequences, right? So you're in the case of the original transformer paper, the cross-attention was with respect to 2 sentences in different languages. But here, the cross-attention is basically the features of the unit, which are the image, and then the embedding that's coming out of these text encoders. So they're basically doing the attention between the text and the image. Additionally, condition the model on the pooled text embedding. Pooled is referring to a technique called pooling, which is where you reduce the dimensionality of something by basically either taking the maximum value of a certain area or taking the average. So there's average pooling and then max pooling. So pooling average CNN. News. I don't know about news. The images. Yeah, so this is the type of image I love to show for pooling. So in this case, you have a feature map or a latent space, if you want to think about it. And here you have whatever 4x4, 16 different numbers, and pooling allows you to take that down to 4 numbers, right? So pooling is all about reducing the total number of numbers so that it's easier to calculate things and faster and cheaper to calculate things. So they're pooling the text embedding. The text encoders have a total size of 817 parameters, 817 million parameters, versus the UNet itself is 2.6 billion. So these don't seem huge, but it's important that they're not huge, right? Because you want to be able to run these on a consumer GPU. If the model is absolutely massive, you're not going to be able to fit it, and it's going to limit the ability of people to use this model. So you kind of have to, there's a trade-off there between, hey, let's make this model as big as possible, and hey, let's make it as small as possible so that we can people can actually use it on their computers at home. A notorious shortcoming of the LDM latent diffusion model. SD1.X entire model was 890 for VAE text encoder and UNet, so it's a lot bigger now. Damn, so you're saying that just the text encoders now, because there's 2 of them, are even just both of those combined are basically just as big as the entire original Stable Diffusion model. Yeah, I mean, I hope I can fit it on a GPU, right? A notorious shortcoming of the latent diffusion model paradigm is in fact that the training a model requires a minimal image size due to its 2-stage architecture. The 2 main approaches to tackle this problem are either to discard all training images below a certain minimal resolution. I mean, I don't know about requires, right? I feel like you can resize the images, right? Discarded all images with any size below 512 pixels, or alternatively upscaled images that are too small. Yeah, I feel like that seems like the obvious answer to that. Just upscale and crop your dataset so that they're all some consistent size. However, depending on the desired image resolution, the former method can lead to significant portions of the training data being discarded. That will likely lead to a loss in performance and hurt generalization. Okay, so this is the type of stuff that you discover when you are doing machine learning, right? Where you realize that, hey, actually in our previous pipeline, we were throwing away like 20% of the data because it wasn't the right image size. So it seems like they kind of discovered that, where maybe the previous models like SD1.X and SD2.X, they were actually training on a subset of all the data that they could have trained on because they were throwing away too much of it. So sometimes the way that you filter your data set is too aggressive, and you realize that you could actually be using more of that data. Discarding all samples below our pre-training threshold would lead to a significant 39%. This is kind of an interesting way to talk about resolution. So normally whenever you see an image resolution, you see it as maybe 256 and then an X and then 256 to be the height and width. But here they're adding this little squared because the total amount of pixels is 256 times 256. But that's kind of a weird way of talking about image resolution with a squared like that. Would lead to a significant 39% of discarded data. Damn, so they were throwing away 39% of the data. Height versus width distribution of our pre-training data set. With the proposed size conditioning, 39% of the data would be discarded due to edge lengths smaller than 256. Yeah, so this is the height and the width of the images, and there's a little bit of a pattern here because generally you're almost never going to see an image that is 1,000 pixels wide and then 200 pixels tall, right? There's kind of agreed upon image resolutions in the internet. You know, most things are kind of square-ish, but it seems like the problem was that because of their aggressive filtering, everything that was below 256 here, which ends up being 39% of the data, was actually getting thrown away. So it's a good catch, whoever found that. Every dream. You can load text encoders onto GPU one at a time. That sounds gross, man. If in order to generate an image, I need to load the text encoder, encode the text, load the second text encoder, encode the text again, load the diffusion model, get that, and then load the refiner model and then get that. Like that, loading and unloading models onto the GPU memory is like, yeah, is one of the slower pieces for sure. Layers are greatly reduced memory needed, so VRAM use isn't as bad as you might think. Huh. Okay. Instead, we propose to condition the UNet model on the original image resolution, which is trivially available during training. In particular, we provide the original height and width of the images as an additional conditioning to the model size. Each component is independently embedded using a Fourier feature encoding. What? We condition the UNet model on the original image resolution. Okay. So now we know what some of these are. So obviously they're going to condition on the text, right? And they're going to condition on two versions of the text encoded with slightly different versions of clip. But then now we know what one of these is. So one of these other what they're calling here vector conditionings is literally just going to be the basically the size of the image. So some number, some information, right, that represents, is this a very wide, huge image? Is this a very tiny, square image? Is this a very tall image, right? So like find a way to pass that information into the model, right? To give that to the diffusion model so that it can condition the noise removal on that information. Okay, so here's the actual H original, W original. So this is just going to be, these are going to be numbers, right? So this is going to be some number from 0 to, or not 0, but maybe 10 to 1,200 or something like that. But how are you going to turn it into a number that's centered on 0 and that has a nice little Gaussian distribution, right? You can't just give a neural net a number like 800 and 600, right? 800, 600. Like the neural net doesn't know how the fuck to deal with that kind of number. So you have to turn it into a number that's a small float that's like hovers around 0, right? And they're going to do that using a Fourier feature encoding. And they're also going to, you see here how they're teasing a time step embedding. So another thing that these diffusion models tend to be conditioned on is the step at which the diffusion model is. So let's pull up our good old diffusion model image here. Yeah, right here. So here you have the diffusion model, right, is working in multiple time steps, right? It doesn't do it in one shot. This is actually a better image. It doesn't do it in one shot. It does it in multiple shots, right? And a lot of times the time step, right, which is this capital T, which goes from 0 to capital T, right? You can feed that time step as well. So you can say, hey, here, remove the noise from this image, conditioned on this text, and here's also the size of the image, and then here's also the current time step, right? And what the time step is useful for is that if you're very early on, like maybe here, right? You want to remove a lot of noise, right? Because you're starting just from pure noise. But once you get to like, you're very close to the actual final image, you don't want to remove as much noise. So the strategy for how much noise to remove should have some notion of like, how close am I to the actual final image? How far along this series of time steps am I? Original crop size as tuple. You're talking about literally what they call it here. Original size as tuple. And then target size as tuple. And then crop chords top left. So it's interesting that basically all of these are information from the beginning of the image pipeline, right? So like normally your image pipeline is going to have a bunch of different things, such as, hey, you crop it and then you take the smallest length and then crop it to that and then make sure it fits this size. And a lot of times that information is kind of lost, right? Like if you were training a classification model, like you throw away that information. No one cares about what the original size of the image was, whether it was slightly thicker, where exactly did you crop it. But it seems like here they're taking those things and bringing them into the actual model. So now you're probably going to have to keep track of these, which is maybe more annoying, but there's information there, right? The more information you can feed into this diffusion model, the better it can do. At inference time, the user can set the apparent resolution of the image via this size conditioning. Okay, so the apparent resolution is this here, is the resolution of the final image. So 1024 by 1024, you're going to basically be giving that here to the base model. So the base model is also going to be conditioned on the this tuple here, 1024 by 1024, or the Fourier encoding of that tuple. Size conditioning, the model has learned to associate the conditioning C size, and that should be green, with resolution-dependent image features, which can be leveraged to modify the appearance of an output corresponding a given prompt. Note that for the visualization in Figure 3, we visualize samples generated by the 512 by 512. This is a little annoying. So you see here how here they're calling it 512 by 512, but here they were doing this squared, 256 by 256 squared. So I would have liked to see a little bit consistency there, but since the effects of the size conditioning are less clearly visible after the subsequent multi-aspect ratio fine-tuning. Multi-aspect ratio fine-tuning. Okay, so they just introduced here that they're doing some fine-tuning as well. So it's not just going to be a one training process, they're going to have a multi-step training process. They're going to probably do some amount of pre-training and then they're going to fine-tune it. Okay, we'll see exactly what they're doing. Okay, but here what we're seeing is this C size, which is the conditioning of the diffusion model using the size of the image. And you can see here how, depending on what you're conditioning with, it actually changes the image. So you see here, when you condition on a very small size, the model produces a kind of a blurry image. When you condition with a big size, the model produces a cleaner, crispier image. Here's the actual text. Robot painted on a graffiti as a brick wall, blah, blah, blah. Yeah, and for example, grass is growing out of cracks in the concrete. When you condition on a tiny image size, it doesn't even show that. But once you have the actual bigger image size, it does decide to paint the cracks and the grass. The effects of varying the size conditioning. We draw 4 samples. A little typo there. It should just be we draw 4 samples or show 4 samples with the same random seed from SDXL. So random seed, right, at some point when you do these, when you perform inference with the diffusion model, you have to pick this random starting point right here, right? You have to pick a random latent to start from. And the latent is sampled, right, from some random process. And that random process is defined by a seed. So anytime you have anything random like that, you're starting from some random thing, you have to basically define this seed, and that allows you to create the same random process again if you need to later in the line. Okay, but they're using the same random seed such that there is no effect of the random latent on this. The image quality clearly increases when conditioning on larger image sizes. I would agree with that. Samples from the here we go, switching again the notation here. I don't know why they keep going back and forth here between the different ways of writing the resolution. We use the 512 pixel based model since the effect of size conditioning is more clearly visible before fine tuning. Best viewed zoomed in. Okay, all right, so now this is making a little bit more sense. So pre-training on training on a big image is much more annoying and much more computationally intensive than training on small images. So I bet you, I don't know for sure yet, right? So far, all we know from the fine-tuning is just these two sentences here. But I bet you what they do is that they train on smaller images, right? So 512 by 512, 224 by 224, and then they fine-tune on the bigger images, right? So it's a kind of a way of saving compute and training cost by just using the smaller images first and just kind of grinding through those for a bunch of epochs, and then using the bigger images, because the bigger images are going to be better. There's more detail, and you're going to end up with a model that can actually recreate the detail a little bit better. But if you had to constantly switch the size of the image, it would be annoying, right? Like if you had a batch that had 224 images, and then you had a batch that had 1024 images, and then you had a batch that had 512 images, like that would make your GPU would just have to work overtime, right? You'd have to constantly be loading different size images, and it'd be more annoying to do that. So that's my guess, is that this pre-training fine-tuning that they're doing here is based on image size. But every dream. They train on 1024 by 512, whatever. It buckets the batches on the fly. Is that what it is, every dream? Is it like starting from lower resolution then going up to the higher resolution, or are you saying that they do all the different sizes at the same time? I wrote the code for this part. That's pretty badass, every dream. Pretty cool that I have or that we have a stable diffusion engineer here. It was on the fly all at the same time. Do you do anything like clever? Like, are you doing stuff like you, depending on the size of the batch, you kind of like you start? It's almost like a bin packing problem, right? Like whenever you're trying to fit things into a box, you put the big things first, and then you fit the remaining space with the little things, you know? So I wonder, you could do the same thing for the batches. Yeah, so basically you fit the big image first, and then you figure out how many of the smaller images you can fit. That'd be pretty cool. It's like, that's like a whole research area, you know? You could probably publish a paper on that, on like optimal bin packing for batch selection of images. The entire batch must be the same size, the same tensor shape, so you bucket them. Yeah. Okay, cool. Good to know. Appreciate the insight. Conditioning on the original spatial size of the training examples improves performance on class conditional ImageNet. So here they're conditioning on a class and trying to generate ImageNet. So this is kind of a way of evaluating the generation in a more kind of quantitative way. Is like, hey, let's try to generate images from ImageNet. And ImageNet has a bunch of different classes like car and plane, right? So you say, okay, let's condition our diffusion on plane and then see how this image of a plane compares to images of a plane that are actually from ImageNet, right? And then here you have inception score, and then Frichet inception distance, and both of these metrics are just based on the idea that the distance in the latent space of an inception model is indicative of the semantic relatedness of two images, right? So lower is better and then higher is better here. But I generally don't like these scores because I feel like the model that they use is kind of old at this point. Like if you actually look at inception distance here, this is a 2016 paper, and they were using an older here inception score deep learning. Yeah, inception score was proposed in the 2016 paper, evaluated blah, blah, blah. Dude, fuck these off. But yeah, what they're doing is the distance with this inception v3 model, which is actually like old. You know, it's like it's not. Do you really trust that inception v3 model? I don't know. I don't trust it. All right, let's go back up. I completely lost where we were. All right. Damn, we're making no progress. We're on like page number 4. We need to be a little bit faster here. We quantitatively assess the effects of this simple but effective conditioning technique by training and evaluating 3 latent diffusion models on class-conditioned ImageNet at spatial size of 512 by 512. The first model, we discard all training examples with at least one edge smaller than 512. So the first one here, this is the technique that resulted, or the dataset filtering that resulted in a 39% removal of the data. So this is basically a lower amount of data. For CIN no conditioning, we use all training examples but without size conditioning. So this is all of the data, but you don't condition on the size. And this is all of the data, but you do condition on the size. So obviously all of the data and conditioned on the size performs the best, right? It has the highest inception score and the lowest Frechet inception distance. But interesting to me here is here you see I don't feel like the conditioning is really adding that much, right? Look at this, 211 to 215, 39 to 36. So conditioning on the size is doing a little bit, but not actually that much. But it is a pretty simple thing to add, so if it works even just a little bit, I guess that's good. We attribute the degraded performance only to bad generalization due to the overfitting on the small training data set. Although we find these classical quantitative scores not to be suitable for evaluating the performance of foundation DMs, they remain reasonable metrics. I love this. Whoever wrote this, these are my homies here. I also do not find these classical quantitative scores to be suitable for evaluating the performance of foundational diffusion models. Because here's another thing too, right? Is that here there's kind of a blurriness to the image, right? I bet you that inception score for ImageNet, it wants the image to be blurry, right? So if you give it a blurry image of a plane, it's going to think that the blurry image of a plane is more like the planes in the original ImageNet than a crispy image of a plane, right? So going from blurry to crispy here, you're changing the kind of like the high frequency or low level features of this image. And part of the distance in the inception v3 model is based on some of that kind of information, right? Some of that kind of like high frequency, like texture information. So you can end up in a weird counterintuitive place where making an image blurrier and shittier, much like the ImageNet images, is actually going to result in a better score. So yeah, that's just one kind of mechanism by which these scores could mislead you. What does Appendix F say? I don't know. What is that in context to? Conditioning. Oh, here you're saying see Appendix F. Sampling steps, clip VITG, plotting FID versus clip score for different CFG scales. This is a classifier-free guidance, right? I think that's what CFG stands for. It's whenever you condition on something and then you don't condition on something, and then you have this like a little toggle about how much conditioning you want to have. clip score slightly better than FID. Yeah, so here they're plotting, this is kind of a weird plot here. Clip FID score compared to clip score. So why would you see this little weird check mark here? Compared to versions that do not align with the judgment of human evaluators. FID are worse than for both, while human evaluators clearly prefer over those previous models. Okay, so FID lower is better, right? So this is saying that you would expect this to keep going down, but it doesn't. However, with the advent of foundational, which are notably targeting visual compositionality, but also other deep tasks, fine-grained distinction between unique artistic styles has pronounced sense of visual aesthetics. Demonstrates that Coco zero-shot FID is negatively correlated with visual aesthetics. I feel so validated, you know, for so many of these paper streams. Like, I've always talked negatively about FID and like I just shit on it, but I never have the like actual precise language to beyond just like analogies. But here you go. Now we have scientific proof. This paper right here. Measuring the generative performance of such models should rather be done by human evaluators. I feel so validated. I was so lost, and now I understand. Hupo's gonna love this. How old is this? Watch this be like a fucking... Okay, no, this is a new paper. Okay. Yuval, Christian, open user preferences, pick a pick. It's pretty badass. You know what we need? We need the ability to like go back. Like, so I clicked on this paper, but now I need to basically scroll up. So if any of you work at PaperPile, like I want the ability to like go back to where I was before. All scores have been evaluated based on 10K generated examples. Yeah, and like maybe this is also a little bit of a tangent, but here we're talking about how like FID is misleading, and my intuition on that is that just if you just improved the model behind FID, right, you just used a more modern model, it would be a little bit better. And now take that same mindset and look at every single place that clip is used in this, right? You're using clip for the text embedding. You're using clip as a metric. You're using, right? And I feel like we can make a better clip. So as soon as someone makes a better clip, you're going to make better text embeddings. You're going to have a better metric to score things with. So I don't know. That makes me excited that as soon as someone makes a better clip, there's going to be so many papers that are going to be able to use that. Okay, going back. I did not go back. Let me go back. All right, condition the model on cropping parameters. The first two rows illustrate a typical failure case. Synthesized objects can be cropped, such as the cut-off head of the cat. An intuitive explanation is the use of random cropping during training of the model. Okay, so obviously when you have weird image sizes, right, maybe like a 600 by 300 or something, whatever this is here, you're going to have to crop it so that it's square, right, because this is trained on square data. And they're saying that I guess when you crop it, you end up with these weird artifacts that the model itself also generates cropped images because that's what it's been trained on. Propaganda poster depicting a cat dressed as the French Emperor Napoleon. Yeah, dude, I mean, just look at this quality. This is so much cleaner. Like SD 2.1, SD 1.5, these still look kind of shitty, but this looks so clean. You even have the holes in the cheese. Like, look at that. Look at how nice the holes in that cheese are. You know? They run a bot on their Discord. Pick a Pick was part of that as well. I agree 100%. Do SD 1.5 and SD 2 share the same architecture? Same architecture, different clip model though. Okay. Close-up of a fire-spitting dragon cinematic shot. This is also cleaner. But I think what they're showing here is not the crops. Here's the real thing though, is that French cheese does not have holes like that. This is Swiss cheese. So that's the real meta right there, is that really what you would want is something like a brie or a camembert, or there's a bunch of different French cheeses, but French cheeses don't look like this. So it still doesn't know that if there was an emperor cat Napoleon, it would have a French cheese, not a Swiss cheese. Okay. We're getting kind of in the weeds though. Collating a batch in DL frameworks such as PyTorch requires tensors of the same size. A typical processing pipeline is to resize an image such that the shortest size matches the desired target size, and followed by randomly cropping it along a longer axis. Yeah, this is kind of the standard way of getting images into the right size, right? You have basically tall images and then long images, and if it's a long image, you basically want to take the shortest side, which is going to be the height, and then make it so that it's whatever your size needs to be. So in this case, 512 by 512, and then crop it from that. While random cropping is a natural form of data augmentation, it can leak into generated samples, causing the malicious effects shown above. So another way of saying this is that images on the internet tend to have an object-centric bias, right? There's a prior in the images that the object of interest is generally in the center of the image, and as soon as the object of interest stops, you generally have basically the end of the image. So it's like the entire cat is within the box. But when you randomly crop, you're basically getting rid of that prior. You're removing that prior, because by randomly cropping, you might end up in a situation where the image is no longer in the center and the boundaries of the image no longer nicely wrap the object in the center. So random cropping effectively erases the object-centric prior that is generally common in images. SDXL buys to Swiss cheese. Yeah. To fix this problem, we propose another simple yet effective conditioning method. During data loading, we uniformly sample crop coordinates, C top and C left. Okay, so this is the final one. So we had the time step embedding, we had the target size, we have the target size, we have the original size, and then we have the last one now is the crop coordinate. So this is the last of the 3 special conditioning vectors that they added. Integers specifying the amount of pixels cropped from the top left corner along the height and width respectively, and then feed them into the model as conditioning parameters via Fourier feature embeddings. It'd be kind of cool to see what that actually looks like. Fourier feature embeddings. I don't know. At some point, I'll look up exactly what that is. Similar to the size conditioning described above, the concatenated embedding C-cropped. So concatenated, they're taking all these embeddings, all these conditioning vectors, and concatenating them together. It's used as an additional conditioning parameter. We emphasize that this technique is not limited to LDMs and could be used for any DM. Note that crop and size conditioning can be readily combined. In such a case, we concatenate the feature embedding along the channel dimension. So it's almost like you're passing it a multi-channel conditioning vector before adding it to the time step embedding in the unit. Given that in our experience, large-scale datasets are on average object-centric. All right, so here's kind of the rant that I went on earlier about the object-centric nature of this. We set C top, C left 0 during inference and thereby obtain object-centered samples from the trained model. Good stuff. By tuning C top, C left, we can successfully simulate the amount of cropping during inference. This is a form of conditioning augmentation and has been used in various forms with autoregressive models and more recently with diffusion models. Okay, so that's kind of cool, right? Where because you've been conditioning this model in training with the actual cropping, you can now, during inference, also give it a value for this cropping conditioning, and it'll generate an image that is cropped. So basically, you can now optionally generate cropped images. I don't know why that's useful. I don't know why you would want to generate images that are cropped, but I guess that's kind of cool. While other methods like data bucketing successfully tackle the same task, we will still benefit from cropping-induced data augmentation while making sure it does not leak into the generation process. We actually use it to our advantage to gain more control over the image synthesis process. It is easy to implement and can be applied in an online fashion during training without additional data pre-processing. So applied in an online fashion during training. What they're talking about here is that sometimes in your image pre-processing pipeline, one way to do it is you basically apply it to all your images beforehand, and then that prevents the need from having to basically keep resizing and recropping images over and over again during training, because that resizing and recropping takes up compute, and that's doing it offline. But you can do it online, right, which means that you do it while you're training. The advantage with one is that, let's say you had a small image data set and you were training on it for 100 epochs, saving 100 versions of the same image with slightly different crops, you're going to blow up the size of your data set at the cost of now you don't need to perform that compute during training. So it's kind of this trade-off of, like, if you have a huge data set, you probably want to do the image processing during training. But if you have a very small data set and you're going to be doing a ton of epochs on it, you probably want to apply some of that processing before training. I don't know, kind of rough ideas there. Well, the common output resolutions for text-image models are 512 or 1024 by 1024. We argue that this is a rather unnatural choice given the widespread distribution of landscape or portrait format screens. Yeah, I would kind of agree with that, that square images are more rare than landscape and portrait images, but this also depends on the data set, right? Because I bet you if you're Meta and you have Instagram, right, you're someone at Facebook AI Research and you're sitting on basically the Instagram data set, Instagram forces you to have square images, right? So in that case, the square images would actually be the natural choice. So I think it depends on the distribution of your specific data set. But Stability AI is scraping the internet, and the internet is I think less so biased towards the square size. But there's a bunch of proprietary data sets like the Instagram that I think are square dominant. We fine-tune our model to handle multiple aspect ratios simultaneously. We follow common practices, partition the data into buckets of different aspect ratios. This is the bucketing that you were talking about, EveryDream, where we keep the pixel count as close to 1024 as possible, varying height and width accordingly. All right, so here we have a algorithm 1, conditioning pipeline for size and crop conditioning. Varying the crop conditioning. Okay, let's look at it. Okay, so you start with some training data set of images D. Target image size for training. Okay, so you have to define what am I actually going to... the final images that I generate, what is the height and width of those images, because that's actually used as an additional conditioning vector. You have some image resizing function R. There's a bunch of different ways to resize images. There's different interpolation. There's like spline, cubic, a bunch of different things, and they kind of trade off. Some of them are more computationally expensive but better, and then some of them are cheaper but computationally cheaper but worse. And a cropping function C, a little typo here. I think they probably just meant cropping function C. Model train step T, converged false. So if converged, while not converged. I guess no, here you're saying you're setting the variable converged to false, and then while not converged, do this, and then at some point you're going to say the variable converged here is going to be here. What's t? Train step t. Okay, so if you've gotten to the final training step, then converged becomes true, and then you break out of this while loop here. Here you're sampling some image x from the dataset D. You're getting the width of the image. You're getting the height of the image. You're putting that into this tuple, just condition tuple, C size. What is R? Is the resizing. So you're resizing the image X according to your target image size, S. So now you have your resized image, X. I would have called this XR. If H original is less than or equal to W original, what is H original? I guess width is less than or equal to or height is less than or equal to width. So find the shortest side. That's what this is. Then resize based on the shortest size. Or sample, okay, no. Here is you're choosing where to crop. So you're cropping based on a uniform distribution. So you're picking a random place to crop, right? You can think of it kind of like if you have to fit a square inside a rectangle, like where do you fit that square? Do you fit it all the way to the left, all the way to the right, or somewhere in between, right? And that somewhere in between is sampled from a uniform distribution, which is just basically a distribution where anything along here. Uniform distribution is uniformly distributed. Yeah, so everybody knows the Gaussian, right? This is the Gaussian distribution, right? You're more likely to select values in the middle. In a uniform distribution, you equally probability of selecting any value within the range. Okay, so you're picking your crop location for the top, also for the height, the width, and then also for the height. And then you're putting that into this C crop variable. Then you're cropping the image. And then you train a model. This is kind of a... You know, I like this. I like that this algorithm tells you exactly what they're doing, but it's also a little bit kind of didactic. I don't know what the right word there is, but like it's just like they're literally... This is just cropping an image. I don't know. I've actually implemented this. I'll drop a link on your Discord. Are you one of the authors of SDXL? Overcomplicating? It's my old Every Dream code. I don't think it's overcomplicated. I just think it's like... I don't know. I like it. I'm not going to talk shit on it because Every Dream is here. An astronaut riding a pig. Highly realistic DSLR photo cinematic shot. A capybara made of Lego sitting in a realistic natural field. I mean, this is pretty fucking good. It's a weird thing to highlight. Yeah, that's kind of the way I would say it. It's like there's nothing wrong with this algorithm. It's just kind of weird to like literally have a half of a page dedicated to how you crop an image, right? Okay, but what are they saying here? Varying the crop conditioning. So if you change the cropping, you can basically cause it to be cropped, which is what we were saying here, right? Where basically they're saying, hey, because we're conditioning on the crop, you can actually now pass it during inference a crop, and it'll crop it for you. So if you wanted a picture of an astronaut pig that is cropped such that the top is gone, it'll actually produce that. But I just don't know why you would necessarily want that. That's kind of a weird level of control for the end user, right? I feel like the end user doesn't actually give a shit about whether or not is not going to want a cropped image. They're always going to want this 0,0 object-centric image. Okay, so varying height and width according in multiples of 64. A full list of all aspect ratios used in training is provided in app Appendix I. During optimization, a training batch is composed of images from the same bucket, and we alternate between the bucket sizes for each training step. Is uncropped output image the biggest contribution of the paper? No. I think there's a bunch of different things that they did here. The biggest contribution of this paper is the result, is the quality of the actual images, right? So this isn't like some papers come out of like a academic lab, and the point is to have like one specific novel algorithmic contribution, right? That's kind of usually what papers used to be, but this is a paper that describes an engineering effort more so to create the best possible generated image, right? So like what Stability AI is interested in is creating the coolest possible image. So the paper is not, hey, let's try to do something weird for the sake of doing something weird and novel. It's let's try to actually do something that makes it work as best as possible. So I would say that's the contribution of this paper is high quality image generation. But then there's a variety of different tricks that they use. And so far the tricks are this kind of conditioning based on the image sizes and the cropping, and then also they have conditioning on 2 different text encoders. And then we haven't heard about it yet, but there's also this refinement model that they talk about, which I think they'll talk about in a second here. Okay. Model receives the bucket size as a conditioning represented by a tuple of integers, which are embedded into a Fourier space in analogy to the size and crop conditionings described above. Okay, we apply multi-aspect training as a fine-tuning stage after pre-training the model at a fixed aspect ratio and resolution to combine it with the conditioning techniques introduced in section 2. Okay, so now, so we're getting a little bit better idea of what this fine-tuning stage is. So there's the pre-training stage and then the fine-tuning stage. Pre-training happens before the fine-tuning. Those words maybe have a little bit more baggage than necessary. Like generally the whole point of pre-training and fine-tuning is you pre-train a model to create a more general model and then you fine-tune it to a specific application. But at this point, that's not necessarily what's going on here. Like here, it's more so there's two stages to the training. I would have just called them stage 1 and then stage 2. But in stage 1, they fix the aspect ratio and the resolution. And then in stage 2, they do this kind of bucketing where they're using different buckets of different target sizes and then conditioning it on that aspect ratio here, CAR, C aspect ratio. Provides Python code. What the fuck is this? Python code? This weirdly written. Note that crop conditioning and multi-aspect training are complete complementary operations, and crop conditioning then only works within the bucket boundaries. Improved autoencoder. Okay, so the autoencoder is the part of the model that actually turns the image into a latent and then turns the latent back into an image. The autoencoder that they're using, so here is the different autoencoders. They have SDXL VAE. This is a variational autoencoder used for SDXL, and then they have the VAE used for 1.x and then 2.x. Here you have different scores, right? So peak signal to noise ratio, PS. I think it's supposed to be PSNR, right? PSNR. Yeah, here it's PNSR. I think it's supposed to be PSNR. But higher is better. SSIM, I think it's like structural similarity index measure or something like that. LPIPS. I don't even remember what that is anymore. And then Frichet inception distance. Lower, lower, higher, higher. So kind of seems like the variational autoencoder they used for this SDXL model is better in kind of every category, which makes sense, right? Bulk of the semantic is done by the LTM. We can improve local high-frequency details by improving the autoencoder. We train the same autoencoder architecture used for the stable diffusion at a larger batch size. Larger batch size, huge proponent of that, because not only are you going through more data faster, but also the gradient steps that you're taking, I think, are more semantically meaningful. This is something I kind of tend to argue for, is that the larger batch size is not just about kind of computational efficiency and speed and volume. It's also about taking better steps, and the optimization process itself is improved by a larger batch size. track the weights with an exponential moving average. The resulting autoencoder performs the original model in all evaluated reconstruction metrics. We use this autoencoder for all of our experiments. I think you can also download this one. So in the actual stability AI, let's open up a new one here. Stability AI, this one here, yeah. They also released the VAE, so here you go. Here's the actual variational autoencoder that they used for this. So here you go. It's only 335 megabytes. That seems really small. I feel like this is also the autoencoder is kind of similar in my head to the text encoder, and I feel like if you used a bigger and better autoencoder, you might actually get much better results, but I don't know for sure. If I use UNet from SD 1.5 but use the autoencoder or the VA from SDXL, will it generate corrupted images or still work? It probably won't work. So the VAE, right, is basically, it's learning this language, right? There's an encoder and there's a decoder, and what's happening is you're basically forcing these two neural nets here, the encoder and the decoder, to learn a language that they can communicate to each other in, right? And you're putting a constraint on the size of this language such that it has to be a compressed low-dimensional representation of this image, right? So the VAE from SD 1.5 has learned a completely different language, right? It's a completely different encoder and decoder. They've learned a different language to communicate together, versus the VAE for XL is going to be a different language as well, right? So like the languages aren't the same. They're unique, if you want to think of it that way. You can't use an encoder with a decoder that's different. You can't use a decoder with an encoder that's different. You got to use the encoder that was trained with that specific decoder, and vice versa. Okay, we trained the final model in a multi-stage procedure. Trained it from scratch, random init each time. SDXL uses the autoencoder from section 2.4 in a discrete time diffusion schedule with 1,000 steps. First, we train a base model on an internal dataset whose height and width distribution is visualized in Figure 2. 6,000 optimization steps at a resolution of 256 and a batch size of 2048. Absolutely monster batch size. Using size and crop conditioning. When you see that batch size, that's parallel. That's why they're using PyTorch Lightning, because it's spread out over a bunch of GPUs. We continue training on 512 by 512 for another 200,000 optimization steps, and then finally do the what they called fine-tuning, but is really just an additional step of training, this multi-aspect training. Okay. Yeah, so actually they're doing everything. So I originally guessed that the training was done first at small resolution, then at bigger resolution, and then at bigger resolution. And that does seem they are doing that, right? You have first at 256, then you train at 512, and then you do this multi-aspect training, which is conditioning on a slightly different thing. So there's actually 3 steps to this training. Empirically, we find that the resulting models sometimes yield samples of low local quality. What the fuck is low local quality? It means the textures are shit. To improve sample quality, we train a separate LDM in the same latent space. Okay, so same latent space here means that they're going to use the same VAE, right? So it's not a different VAE, it's the same VAE. And the reason you would do that is so that you don't have to basically, like, let's say that you were here. If your refiner model used a different VAE, right, a different latent space, you would have to take this latent here, you would have to convert it back to an image, and then take that image, encode it into the different VAE, and then put that into a refiner. So using the same VAE for both the base and the refiner just makes a ton of sense. Okay. Based on a which is a specialized on high quality, high resolution data, and we employ a noising denoising process as introduced by SDEdit on the samples from the base model. High quality, high resolution data, so probably just images that are 1024 by 1024 if I had to guess. We follow one and specialize this refinement model on the first 200 noise scales. During inference, we render latents from their base and directly diffuse and denoise them in latent space with a refining model using the same text input. This step is optional but improves the sample quality. You know what? It might also be the case that this is actually what adds the watermark. I've heard that they have a watermark for these stable diffusion models, so which model is adding the watermark? The base model or this refinement model? To assess the performance of our model, we conduct a user study and let the user pick their favorite generation from the following 4 models. Or is it the VAE that adds the watermark? SDXL, SDXL with refiner, stable diffusion 1.5, 2.1. Okay, this is the actual human study where they let their users pick their favorite generation. Here we have what is this? 1024 squared, so the highest resolution that they have, with and without the refinement model. Okay, so without is left, and then with is right. So I guess what they're showing here is that this resolution or this refinement model makes the smaller details clearer. So you can see here how the leaves in the trees are slightly better. The ripples in this water are slightly better. The kind of like details on these skyscrapers are better as well. You get a little bit more of a sense of depth, and this like misty kind of like fog effect is a little bit cleaner versus here. The skyscrapers kind of like blend into each other. Something interesting is like when people prompt these image generation models, right, they'll use something like 8K, right, which refers to images that are rendered at a very high resolution. But the interesting thing to realize is that none of these generative image models were trained at an image resolution of 8K. So all the images that have 8K in the caption have been downsampled from 8K into whatever the diffusion model is being trained at. So it's kind of interesting how, like, even though people use 8K or 4K or Unreal Engine, like specific keywords, it's this specific keyword of 8K. I don't think any generative image model has ever seen an 8K image because they're always downsampled. Future work. This report presents a preliminary analysis of improvements to the foundation model stable diffusion. While we achieve significant improvements in synthesized image quality, prompt adherence, and composition, in the following we discuss a few aspects which we believe may improve the model further. We generate the best samples using a 2-stage approach with an additional refinement model. This results in having to load 2 large models into memory. Yeah, it's kind of quite annoying to do that. And you know, I think this is kind of what I was talking about before, but if you're Stability AI, it's not, you know, like Midjourney doesn't care because Midjourney is just providing a service. So they can have many different models in their pipeline and, you know, they deal with that on their cloud and they make sure that they have the right kind of system set up in their cloud such that you don't have to keep loading and unloading a model. But Stability cares more about kind of the end user is someone who's actually performing the inference themselves on their own hardware. So now you have to think a little bit more deeply about, okay, is having to load 2 separate models worth it? Yeah, hampering accessibility, I guess, is the trade-off you have to consider. Text synthesis, while the scale and the larger text encoder help to improve the text rendering by incorporating byte-level tokenizers. What the fuck? Or simply scaling the model to larger sizes may improve text synthesis. Yeah, so making a better using a better text encoder. I think it's just a matter of time before we have much better text encoders that have better tokenizers as well. There's too much money going into natural language processing and creating very good text encoders that I feel like it's just a matter of months before we get a better clip. Like, I could see that coming out by 1 year. During the exploration stage of this work, we briefly experimented with transformer-based architecture such as UVIT and DIT. Okay, so they're still using the UNet, although it sounded like they added some custom stuff to their UNet, but yeah, kind of the TLDR of like model architecture is that it actually doesn't matter anymore. It used to be there used to be a world where like model architecture was actually everything, you know, and like the entire paper was about one little trick in the model architecture, one little difference that you did. But then over time, it became harder and harder to improve performance by changing the model architecture. And now model architecture is just kind of like a detail that no one cares about, you know. It's almost like the optimizer or the learning rate or something like that, where it's just you just kind of use whatever and it doesn't matter. Careful hyperparameter study. While improvements over the original are significant, they come at the price of increased inference costs. Future work will focus on decreasing the compute needed and increasing sampling speed. Yeah, so actually, this is the previous stream that we did, which is 2 days ago. We saw basically 2 different research groups that came up with a faster version of the segment anything model, right? I think FastSam. And what both of these approaches ended up doing is they basically ended up replacing the image encoder in the segment anything model with a smaller version of it that was distilled, right? So what does that mean? What it means is that they took let me pull up the paper here. This is not what I want. I want faster Sam. Look at that. Holy shit, it's my paper. It's my YouTube video. I want this one. Yeah. So this is the thing. This is the segment anything pipeline. It kind of has 3 different models here. You have your image encoder, mask decoder, and prompt encoder. And what they did is they took this image encoder that is actually quite big, and then they distilled it into a smaller image encoder. So they took a small vision transformer that's much smaller than the original VIT that they used in the segment anything paper, and then they basically distilled it. And what that means is that they freeze it, and then they feed an image into it. You get an embedding, and then they feed that same image into a small VIT, and then they have a loss, which is saying, okay, this image embedding should be the same image embedding as this. It's almost like you're copying, right? You are taking the small model and you're training it to just copy and mimic the big model. And you do this enough times, and eventually you're going to get this small version of the image encoder that kind of basically is the big version of the image encoder, right? It has figured out some way of converting images into image embeddings that are virtually identical, ideally, right? They're still going to be a little bit different to the image embeddings that you would get from the big image encoder. So a similar kind of technique could be done here, right? Where, hey, you could take the different parts of this, specifically the VAE, or maybe, I don't know if you could do this with the actual UNets, but like even just doing or using making the VAEs much smaller through distillation could be a way to save VRAM. And not only could you do distillation, but you can do distillation and then use quantization on top of that. So that's like a double whammy, right? Where quantization is a way to make models smaller and faster, and then distillation like this is a way to make models smaller and faster. And you can stack those. Those 2 techniques can be applied together. So that could be a way to get a very, very small version of a VAE that you could then put into here, and it would allow you to run this on a much smaller computer. They don't cover the denoising stuff at all. They did a lot more work. Maybe Robin Andreas will make another paper on that later. So you're talking about the sampler and stuff like that. Train on discrete time formulation and requires offset noise for aesthetically pleasing results. The EDM framework of Karras is a promising candidate for future model training, as this formulation in continuous time allows for increased sampling flexibility. Did we read this paper? I feel like we read this. I'm not 100% sure. Let me see. Kind of vaguely remember this. I don't know. Let's see. Yeah, I think we did read this. Okay, so there should be a stream about this, but this guy is very good at math. He had another paper where he basically talked about how there's all these different parts of the diffusion models that most people are just kind of using the default choices, but there's all kinds of different trade-offs here. So see all this crap, like the exact way to get the noise, the exact sampler to use here, input scaling, output scaling, schedule training. The schedule that you're using for the noise is also, you can be very tricky with that. Right, like look at this noise schedule where it's like, oh, you just give it the time, and that'll basically the further along in the time, the more noise and so on. Or you can have like this incredibly complicated noise schedule. Like look at that. You have two different hyperparameters here, beta D, beta min. So now you have two extra little numbers to tune there. I don't know, dude. I already forget everything in this paper. The Hune sampler. It gets pretty intense pretty quick. Karras is GOAT. Yeah, I agree with that. Okay, so we're all pretty much at the end here, but let's see what else they got here. Oh shit, look at this. Finally, here's the diffusion model section. Okay. So this is kind of cool. Actually, it used to be that this section here is generally called the kind of background section, and they'll put it at the very beginning of the paper right after the introduction. And sometimes it's annoying because you basically end up reading the same section over and over again. Every single diffusion paper will have this section, but here they actually put it in the appendices, which is, I think, cleaner, you know? Consider continuous time DM framework and follow the presentation of Karras. Karras? I don't know how to pronounce that. Denote the data distribution by adding variance, Gaussian noise. Probability flow ordinary differential equation. Dude, this is dense. let's just scroll away from that. Okay. Thank all the folks who worked on this code. Alex, Goodwin, blah blah blah. Every dream, you're one of these people. We also thank ChatGPT for writing assistance. I love that. I love that they thanked the ChatGPT. So here there's some issues. So obviously you want the piano to be black, but the bench to be white. But then once you say white, it kind of makes everything white. TV shows a lion hugging a giraffe. Yeah, so it just has giraffes and lions everywhere, but it's not putting the lion and the giraffe specifically in the TV. This happens in Midjourney as well, though, right? Like if you say person A and then person B, it'll just give you like a weird mix between both of those people. You know, like if you say Elon Musk facing Mark Zuckerberg, it'll just be like a weird hybrid of Mark Zuckerberg and Elon Musk. Model may encounter challenges when synthesizing intricate structures. You're not on this? Every dream, you gotta get on this. Gotta put your name on that. I know it's kind of political, and a lot of times, like, the fucking getting your name on a paper is just like this giant political quagmire, especially if you're ordering yourself within that, but it's worth it so that you can put it on your resume, you know, and then you can get jobs. Model achieves a remarkable level of realism. I guess if you have code commits, you're fine, right? If you have commits to this repo, you can also always just point to this repo and be like, hey, I'm one of the people that pushed code in here. Heavily relies on large-scale data sets. Or model exhibits notable strengths but is not exempt from certain limitations. Synthesizing intricate structures, achieving perfect photorealism, addressing biases, mitigating concept bleeding, and improving text rendering highlight. I would say that that's not specific to Stable Diffusion, though. These are problems with every single generative image model, and to me, they're almost more coming from the data sets, right? I think that everyone runs into the same issues because everyone's using the same data set, which is largely the internet, right? I think that the way that we're going to solve these techniques is not with the way that we're going to solve these problems is not with some cool special loss or additional training technique. It's going to be basically we're going to wait and the data set is going to get 10 times bigger and then it's just going to magically be solved. So I don't know if you necessarily need to do future research and optimization to solve these things. I think you just wait until the data sets get 10 times bigger, 100 times bigger, and then they'll just magically go away. And you won't have those problems anymore. Left months ago. Did you leave because you had other cool stuff you wanted to do, or did you leave because you were like, these people are fucking toxic and I hate working here? You don't have to answer that question, by the way, every dream, if that's a loaded question. TLDR, working with Stability AI. Thumbs up or thumbs down? Other cool stuff? Okay, all right. Good to know. No, they're all good guys. All right. All right, you know? Hey, I mean, I do that all the time. You know, if you look at my resume, I constantly leave my jobs chasing some other shiny thing, you know? I have never been fired. Let the record show that. Never been fired. I don't even know if I've ever missed a homework assignment, you know? Give the true answer in the Discord. Emad Mustak is like sitting behind you right now with a gun and he's like, don't say it. Don't say it. Okay, I feel like I'm just too tired to go through this math right now. Distribution over noise levels. Denoising, score matching. Langevin diffusion component. Ah, the standard Wiener process, of course. I'm way too tired for that. I'm just going to skip that. Cat drinking a pint of beer. Ooh, this is not good. It's like kind of in the beer. DALL-E 2, SDXL. So really the big difference is here, Midjourney versus SDXL. I would say it's pretty much on par. This is even better. Look at this. It actually, here the penguin has like hands, which is kind of disturbing. But here, Stable Diffusion XL knows that penguins don't have hands. They have flippers. Ooh, and this is also, look how much cleaner this is too, right? Look at the text. This is almost correct versus the text in Midjourney is just complete nonsense. Verg T Vepting Erpen. Here is, I guess, user preference for SDXL in blue and then Midjourney in orange. So actually, SDXL is very good for food and beverage. That's kind of interesting. Not as good for abstract, but I guess abstract is a little bit harder to judge anyways. And it's the worst at properties and positioning and linguistic structures. Very good at imagination and writing in symbols. What is the difference between linguistic structures and writing in symbols? Isn't that the same thing? Single and two-stage, so whether or not you're adding the refinement model. Yeah, refinement model does seem to improve the face. It changes the face, though. See, the face here is this face is better, but it's like it's not even the same face. It's a different face. Lego capybaras. Or no, capybara made of voxels. So it's kind of like a Minecraft type look. This is clean. Look at this. This is a kangaroo holding a sign that says SDXL, and it's like it's almost perfect. SDXL versus SD 2.21 and SD 1.5 are basically nonsense. This isn't even a kangaroo. This is a guy. I've always thought the clipping text encoder could be a sort of bottleneck. I've constantly seen papers that say it's not really good at capturing spatial prior. Yeah, that's kind of what I'm saying, is that like some of these issues that these generative models have, like I'm pretty sure if you just made the text encoder better, they would just disappear. If you just increase the data set size by 10 times, they would just disappear. So I don't think we're missing anything fundamental in terms of like the algorithm or the pipeline or the kind of steps that we're doing. I think what we're missing is just the scale, right? Which is the whole Rich Sutton bitter lesson, is that we just need a text encoder that's been trained on 10 times the amount of text data. We just need a VAE that's been trained on 10 times the amount of image data. And then at that point, this same exact diffusion technique would work perfectly. Text encoder is pretty fast. Here's all the different aspect ratios. Eigenops. Conditioning concatenation along the channel axis. Batch size 16, pool dimension 512. Classical sinusoidal time step embeddings, commonly used in diffusion models. Batch of integer scalars. So this is the tuples. Oh my god. This is what I wanted, though. I wanted to know what the fuck this Fourier embedding is. Fourier embedding integers. I don't think I'm going to be able to find it. Concat embeddings is just concatenating them all together. See how you're concatenating them on the channel dimension here? Because the first dimension is the batch, and then the next dimension is the channel. And then that's it. fast Fourier transform? FFT? Probably. But actually here, we can actually go here. Let's look for this. We can come here, search. What is it called? Fourier embedding. Like, is this? It's not there. Right? Like, is this their own custom thing, or are they just using... What do we do this? Generative AI Fourier embedding. GitHub. Show me that implementation. Jesus Christ. Where is it? Where is that? Fourier Feature Networks, FFN. Yeah, I think it might just be this. That's probably what it is. Search. Sine. Single step, sine scheduler. No, this is cosine, sine. I think this is it right here. Sine, instance, missing, diffusion, autoencoder, sine. I think it's this. Get time step embedding. Yeah, it's this one right here. This is only for the time step, though. There should be one for the actual tuple of crop sizes and image size. Right, you see this assert statement here? That tells me that they wanted to make sure that you only do this with the time step variable, right? Because the crop size and the image size is going to be a tuple. The size of that is going to be 2. So there probably was a situation where someone accidentally passed it into here and they were like, oh, we're supposed to use a different function for that. Attention block. Wow, they actually implement their own attention here. Or no, never mind. Here it is, scaled product attention. Okay, at this point, I'm just kind of like scrolling. Let's do a little summary here. Okay, let's summarize this paper and then we can head out for the day. Okay, let me take a sip. All right. So today we reviewed SDXL, which is the latest version of Stable Diffusion's generative image models. These are models based on diffusion, which is this idea of removing noise from an image to create a final image over a series of time steps, except they're not removing noise from an image, they're removing noise from a latent. And a latent is a small kind of, think of it like a compressed representation of that image, which is coming from a variational autoencoder, which has been trained to basically compress these images. And they train a new variational autoencoder as part of this paper. So this VAE is new with the SDXL. They also train a new base and a new refiner. The refiner is basically also a diffusion model, except it's trained at a high resolution and it's only applied for basically, I think, one step. I'm not exactly sure. I forget. But basically, the whole point is to take the output of the base model and then just refine it a little bit, and it produces a higher detail. But the negative is that you have to now load a separate diffusion model. So you have two diffusion models, this kind of two-step pipeline that they're talking about here. What else? Another interesting thing they did in this paper is they have two text encoders, and then they also... so the text encoders are what convert the text, which is this, for example, this text here of what you want to see. This text is getting encoded and turned into basically a little vector of numbers that represents that the meaning of that text. They use two separate text encoders and then use that encoded text to condition the diffusion process. And an additional thing they do is they also condition it on information about the image itself. So the size of the image and the whether or not it's been cropped, and then the aspect ratio. So a couple different things that they're adding there, which gives you for free the ability to basically generate cropped images if you really wanted to. So if you wanted to generate a picture of a astronaut riding a pig when it was cropped, Stable Diffusion XL can do that. A bunch of different little tricks, but I think the TLDR is that it's actually quite good. It actually produces very good images, and they have a user study to show that it's pretty much comparable with Midjourney, which up until this point was like the king of generative image generation. But it seems like SDXL is pretty much just as good, if not better, in some ways. So looking forward to the heat in the kitchen getting turned up. You know, I'm sure Midjourney is going to try to release a version that's better. I don't know what Midjourney V6 is going to look like, but hopefully it's better than SDXL, but we don't know yet. So that's pretty much it. Kind of running out of steam here, but thanks everybody for asking questions. Every Dream, ASDF, some Korean name that I can't identify, I'm sorry, and Majestic Gizzle or whatever. Thanks for the questions. Thanks Every Dream for giving us context and giving us the secret insider scoop. Hope you guys enjoyed this stream. Like and subscribe. Join the Discord where we can you can recommend more papers. And if not, see you guys, I think on Monday. I think we have a stream on Monday, but have a great weekend. And thank you for watching.